Hey guys, and welcome back to this episode of Curious Scientist. In this video, we will derive the solutions for the particle in a box quantum mechanics problem. Now this is the simplest quantum mechanics problem out there, and to solve it, we will have to use the time-independent version of the Schrodinger equation that we derived in a previous video. So the time-independent version of the Schrodinger equation is written as follows: minus h bar squared over 2m d squared phi by dx squared plus v times phi equals e times phi. And just to run over what the terms in this equation mean, phi is the wave function. What its physical significance is not really relevant to this video. Suffice to say that the modulus square of the wave function gives the probability that the particle will be found in a particular position. V is the potential, which defines the energy landscape of your particular problem. And E is the total energy of the system. The term on the left uses h bar, which is Planck's constant over 2 pi, over 2m, where m is the mass of your particle, times by the second derivative of the wave function. Now, to sketch out what the particle in the box looks like, what this diagram shows is the energy landscape of our problem. Inside our box, so this bit here, the potential is 0, but outside the box, so this bit here and here, the potential is infinite. And this means that outside the box, even in a quantum mechanical world, there is a 0 probability of finding our particle. Now, because the potential inside our box is 0, this means that we can rewrite our time-independent Schrodinger equation without the v phi term, and then we can rearrange the equation. Now, this differential equation is one that we will have seen before. These are the solutions to the simple harmonic motion systems, which are of the form d squared phi by dx squared equals minus k squared phi. And in this case, k squared is equal to 2me over h bar squared. K squared equals 2me of h bar squared. Now, the solutions to our simple harmonic motion equations are as follows. Phi equals a cos kx plus b sine kx. We can also say a few things about the boundary. We can say a few further things about our problem, the first of which is that phi of naught is naught. This is to say that the probability we will find our particle at x equals naught is itself naught, and that's because the potential at this point is infinity, and would mean that our particle would have to have infinite energy. And again, even in a quantum mechanical world, this is not possible. We can say the same thing at a, that phi of a equals naught. The first boundary condition is satisfied by discarding the cos kx term, and this gives our solution in the following terms, that phi is equal to b sine kx. And the second boundary condition is satisfied by saying that ka is equal to n pi. So we now have two equations in terms of k, and we want to substitute in the first equation into the second, so that we can derive the results about the quantization of energy in this system. We can say that k squared a squared equals n squared pi squared, and by substituting in k squared from the bottom left, we can say that 2me a squared over h bar squared is equal to n squared pi squared, and then rearrange to get in terms of the energy. So the energy, E, is equal to h bar squared pi squared over 2ma squared times by n squared. Now what's important about this is that the energy cannot take any value it pleases. It can only take certain discrete quantized values. These quantized states are known as the stationary states of the system, since they are solutions of the time-independent Schrodinger equation and determine the probability of finding the now quantized particle in various positions in the confining region. So to recap, what have we done in this video? First, we've looked at the time-independent Schrodinger equation and how it relates to our system. In our system, the potential is zero, so we have eliminated the v phi term here. Doing this gives us a more simple differential equation to solve. This one here. And we have found that the solutions to this differential equation are the same as the solutions to simple harmonic motion, so that the wave function has solutions in terms of cos and sine. And then, by applying our boundary conditions, such that phi of naught is naught and that phi of a is naught, we have eliminated the cos kx term, and we've said that ka is equal to n pi. And then we had two equations with k, which we substituted into each other to get an expression out for the energy of the system. And we found that the energy of our system is quantized. You've been listening to a Curious Scientist video. If you liked it, don't forget to hit that subscribe button so that you can get new videos just like this every week.